Hello, everybody, and welcome to another great day of physical chemistry. So last time we were talking about our good old friend, the s orbitals, which, are wonderful because they have no angular momentum. However, today, well, things are going to have to actually start moving as we talk about our p orbitals. So again, as a reminder, these are going to be our first set of orbitals at which we have to really bring in our spherical harmonics, is we're going to have to set our L value, or our angular momentum quantum number, to 1. So this means we're starting to see some actual directional movement around the nuclei. So as a reminder, we can go ahead and separate out our general wave function into a set of radial wave functions for, again, our p orbitals, and a set of spherical harmonics for our p orbitals. And radial portion is actually going to be treated fairly much the same way we did for the s orbitals. We're going to look up the radial function, look for the number of nodes, should be able to get the distribution. Big note, for an s orbital, n of 1 has no nodes, and then we add one node for radial node for every integer we increase our n. For p orbitals, since we have no n of 1, we start with an n of 2, second shell. At this point, we're going to start increase, our second shell will have no radial nodes, and we'll see increasing numbers of radial nodes as n goes up. However, we're going to more focus today on our spherical harmonics. So one of the biggest things we have to watch out with our spherical harmonics is when I had an L of 0, well, I only had one possible M sub L. 0. Here, well, I've got three different M sub L's can deal with: 0, 1, and -1. And each one of these will have a slightly different dependence upon the angle of the system, and thus slightly different shapes. So we're going to start with the simplest case, and this is where our M sub L equals 0. So we can then go ahead and look up our spherical harmonic for the L equals 1, M sub L equals 0, and then go ahead and insert this in as our radial or angular portion of the wave function. So when we do this, we can divide it up into two key bits. The first of which is everything that doesn't depend on an angle. So this is, of course, our radial portion, but also don't forget we have a normalization constant for the angular portion as well as the radial. And all this really leaves me behind with is a function that has a dependence upon r and a cosine theta. So cosine theta is the only angle variance we find in the system. So let's go ahead and take a closer look at our notation in spherical coordinates. So we see no dependence upon phi. So this is going to be rotation in the xy plane. So if I look around in the xy plane, this function is completely symmetric. Any angle of phi is as good as any other angle. However, where the fun happens is, again, with the theta. So if I start at a theta of 0, I'm going to have a positive value. If I go to a theta of pi, I'm going to have a negative value. And at a theta of pi halves, so right here around that xy plane, the wave function goes to 0. So this means that my system has essentially an angular node going straight through the middle in the xy plane. And my maximum probability density, or square of the wave function, will occur at the top and the bottom. So essentially, when I'm in the z plane. And it will occur more when I'm in the z plane as far away from the xy plane as possible. Well, this means I'm going to have a positive maximum along the positive z-axis and a negative maximum of the wave function in the negative z-axis, and almost nothing in the xy plane. Yep, this should look familiar. This is our good old pz orbital. And that's how we pretty much get the pz orbital. Because I've got no angular momentum, essentially pointing, essentially because I've got no angular momentum pointing in the z direction, that means that all my motion has to be in the z direction, as it's going to be going up and down and up and down. And this rotating motion should then possibly present a angular momentum somewhere in the xy plane. Which way? Don't know. Schrodinger's equation and Heisenberg's uncertainty principle says I don't know, because it turns out px and py commute. So if I knew it, if I know one, I know the other. That's impossible. So Heisenberg says this is the most we can know. I've got motion in the z-axis, and all of my angular momentum is somewhere in the xy plane. However, what we can then do is, now that I have a set of spherical harmonics for the pz orbital, I can then make this work for the n equals 2 system. So this is my 2pz orbital, where I can insert my radial wave function, combine it with my spherical harmonic, and I get what's honestly not too bad of a function. I have a rather messy normalization constant that is going to actually depend upon the charge of the atom. I have a dependence with R. I have a dependence with theta. And again, I have this slowly sloping down negative exponential at long distances. So I see a straight line near the nuclei of increasing probability density, and then a slowly tailing exponential at far distances. However, one of the things I do want to make note of is that note that the general shape of the pz orbital is not going to depend upon the n. The only thing that's going to happen as I change n is I'm going to change my polynomial term, and, well, actually that's it. I'm going to change the polynomial term because the exponential stays constant. So this actually gives us a cool description of the behavior of any general pz orbital. However, this does leave us with the pesky problem of I have 3 p orbitals: L of 0, m sub L of 0, m sub L of 1, and m sub L of negative 1. Well, what do the other two look like? Well, it turns out that if I have a positive and a negative m sub L, they're going to give very similar wave functions. And this is going to be true for p orbitals, d orbitals, f orbitals, g orbitals. Doesn't matter. They're pretty much going to give me a symmetric set, where the only thing that's going to change is the sign. So I get to keep my same sort of normalization, same sort of radial distribution. And since this isn't going to change, we're going to go ahead and factor this out and abbreviate as I focus solely on my angular portion. Now, while I'm focusing on this angular portion, I'm also going to ignore my normalization constant for the spherical harmonic, just for the sake of convenience. However, I'm going to leave behind a square root of 2, and this posit for reasons you'll see later, and these positive and negative signs, mostly because they differ based on whether I'm +1 or -1. So this is going to seem a little bit odd, but if I have an m sub L of +1, I have a negative sign out front. And if I have an m sub L of -1, I have a plus sign out front. But what turns out to be more important isn't what sign's out front. It's we've got an exponential term here. Because here I have a wave function that has sine theta. So this means I've got no probability density along the z-axis, because when theta is 0 or pi, my density goes to 0. And I'm going to have maximum sort of density along the pi halves theta. So this is around the xy plane. And this kind of makes sense because in the pz, all my density is along the z-axis, which means that there's no more room for electrons along the z-axis because I have an orthogonal set of orbitals, so they have to go somewhere else. So they spend their time around the xy plane. Now, what's probably the weirdest portion about the m sub L plus and minus 1 orbitals is their dependence on phi. Because it turns out their dependence on phi is based on an imaginary exponential. Now, if we go back to our imaginary exponentials, remember that these have essentially a uniform probability density. So this means both of these orbitals have maximum density around the xy plane, but uniform density. So how are they different? And that is actually all about the direction. Because if you remember, if I apply my momentum operator to an imaginary function, in this case, it's going to be my angular momentum operator to this imaginary function of phi, what we're going to find is that if m sub l is plus 1, then what ends up happening is the electrons are going to move in a clockwise direction and generate a positive angular momentum. If they have a negative m sub l minus 1, then they're going to move in a counterclockwise direction and generate a negative angular momentum. If you want to help kind of illustrate this, go ahead and take out your hand and use the right hand rule. See how the electrons are moving around. So what we kind of have for our m sub l's of plus and minus 1 is more or less two ships passing each other in the night. One moves clockwise, one moves counterclockwise. And because of this difference in movement, they can exist in the same spatial they can exist in the same physical space because they really don't interact with each other. And this is kind of a cool feature of these two orbitals. However, these are not the two orbitals you've often been taught. You've been typically taught the px and the py orbital. Px orbital exists along the x-axis, py along the y. Turns out these two functions are not eigenfunctions of angular momentum. They are, however, eigenfunctions of energy. Because what we can do is we can take our m sub l plus and minus 1 orbitals and use a linear combination to generate a new set of orbitals. Again, still have an n of 2, still have an L of 1. So this is kind of like how when I had a particle in a box, it was impossible to put a particle in a box without forwards and backwards momentum. However, when I have this forwards and backwards momentum, I start to see the particle localize. And we're doing something very similar with the px and the py orbitals. So what I can do is I can combine my forwards and backwards momentum. So I can take, I'll take about 50% of my particle moving backwards. So again, my c is going to be 1 over square root of 2, because that way c1 is 1 over 2. So 50% this, and 50% movement in the positive direction. Now, one of the things to note here is that it turns out I'm going to be subtracting these two. That turns out to be okay, because remember, when we're talking about probability density, we're taking the square of the coefficients. And the square of negative 1 over square root of 2 is still, well, 1/2. So it doesn't actually matter what the sign is in order to get 50% of one, 50% of another. But it does turn out that how you combine these two, whether adding or subtracting them, will give you a slightly different shape. So if I subtract these two wave functions, I can then insert my my expression of 1 over square root of 2 sine theta e to the I theta. So when I do this, I'm going to pull out the sine theta because that is shared with both functions. And then my e to the I, then what I end up getting is e to the I theta plus e to the minus I theta. Well, hopefully this expression looks fairly familiar because this is cosine theta. So I now have a function, new wave function that's still a 2p orbital because it still has the 2p angular wave function, but now it or radial wave function, but its angular motion now has a sine theta. So again, sine theta again means that I'm localized around the xy plane, or but a cosine phi means that now I'm going to be localized when uh, when phi is 0, 0 or pi, with a positive value in when it's 0, so pointing in the x direct axis, and a negative value when it -1, well, it's pointed in the negative x direction. And so when we do this, we end up with, again, a 2px orbital. All of my probability density is along the x-axis. The sine theta term indicates I've got no probability along the z-axis, and the cosine phi means I've got no probability density along the y-axis. So this is actually a cool way how we can reconstruct a physical orbital with no imaginary components as a linear combination of our two actual eigenfunctions of angular momentum. However, it is worth noting that we do get some unfortunate side effects of this if I'm trying to essentially apply my angular momentum operators to the 2px orbital. I have to deal with the fact that this orbital is not a true eigenvector, but instead it's a combination of the eigenvectors, and we have to apply our math accordingly. However, just as we were able to generate a 2px orbital, we can also generate a 2py orbital. The linear combination is just a little bit different. Instead of essentially subtracting out our positive e to the I theta, instead we're just adding the two functions together. When we do this, what we end up with is a wave function based on sine theta and sine phi. And when we do this, we're going to have our maximum probability density pointing along the y-axis. However, one of the things that I do like to emphasize is while each of these three orbitals are going to be pointed in a different direction, they do still have all the same radial contributions. So I do want to take a quick moment to revisit our radial contributions. So when I have a n of 2 and a L of 1, so this is our 2p orbitals, what we've essentially done is I've increased the angular momentum of this orbital with respect to, say, the 2s orbital. But as a consequence, what I've also done is, since more of my energy is caught in angular momentum, which is again a positive or a detrimental effect, it means that I need to have a greater potential energy to set it off, as opposed to, say, the 2s orbital, which only experiences essentially an attractive potential energy term. So as a consequence, what we find is that the 2p orbital is actually going to be, on average, a little bit closer than the 2s orbital. This often goes against what you are commonly taught in Gen Chem, but it's an important feature that we'll be talking about much more later. And so consequently, what we find is that as L increases, and this is going to also be true for d orbitals, what we expect is that the average distance of the electron is going to slowly go closer as compared to an orbital with the same principal quantum number, but a smaller angular quantum number, because more of the energy has to be caught in the attractive potential. So again, larger L, closer it is to the nucleus on average. However, I do like to emphasize this on average term, because one of the things that you can note is, let's go ahead and compare our 2p orbital versus our 2s orbital. So our 2s orbital, it has a most probable density for its wave function. So it's most commonly found further out than the 2p orbital. But a very crucial factor happens here. which is I have this peak right here at the nuclei, which means that while on average an s orbital is further away than a p orbital, it does spend an not insubstantial amount of time right next to the nucleus. And this is going to play some crucial roles as we move on and talk about multi-electron systems. But for now, I just want you to be aware of it. So one of the last things I want to address is that, again, we've just been talking about the 2p orbitals. And it's going to be true that all of my p orbitals are going to share the same exact spherical harmonics, no matter what the n is. However, what we are going to find is that as the n increases, what we're going to do is increase those numbers of radial nodes, those areas of high probability density right near the nucleus. So we're going to find little nodules close to the nucleus. However, most of the probability density is still going to be in that big tailing region far away. One of the biggest reasons why is because when I integrate over all space, while I may have a very high wave function near the nucleus for my radial function, turns out when you try and integrate it over 360 degrees, there's just much more volume further out here. So on average, we're going to find a lot of most of the time, the electron is going to be fairly far away from the nuclei, but it will spend a substantial amount of time in these little nodules close by. And you can predict the number of nodules simply by knowing the principal quantum number and the angular momentum. So if I have an n of 2, L of 1, I've got no nodules, and I have a classic barbell shape that everybody knows from Gen Chem. However, when I go to an n of 3, I introduce an additional nodule close in, and we have, well, let's be frank, a kind of distorted shape. Little bit of probability density, bigger section of it further out. However, when you go to n of 4, well, pretty much what you've done is you've shrunk the amount of electron close to the nuclei, and in compensation, you just add on another one of these big mushroom tops to the top of your existing wave function. So being able to just read the quantum numbers and know the approximate shape of the electron density is a very useful feature going forward. However, we aren't just finished quite yet with angular momentum. So far, we've built up the p orbitals, but we still have that good old L of 2. Next up is d orbitals. Till then, take care.